When the temperature rises, the expected threat is water creeping up the beach. But the secondary shockwaves of a warming planet are often stranger. What's striking is how these unexpected collapses take entirely different forms. Writing in the Atlantic, Christian Elliott watches the physical Earth give way, tracking how melting permafrost and shifting water weight cause entire mountains to literally crumble and slide. Then in the Diplomat, Olya K-Mehri looks at a quieter erosion in Tuvalu. Long before the ocean swallows the island, a well-meaning climate migration lottery with Australia is quietly draining the nation of the nurses and teachers it needs to function. When Australia offered a climate migration lottery to Tuvalu, it looked like a humane escape route from rising seas. But writing in late July, Olya K-Mehri shows how the deal is quietly draining the island of the nurses and teachers it needs to function. Notice the brutal math K-Mehri points out. In a country of just 10,000 people, losing a single randomly selected dentist can wipe out a huge chunk of an entire profession.
Australia's climate mobility pact with Tuvalu is often presented as a humane answer to a problem international law has barely begun to confront: how to give people a safe, orderly choice to move before their homeland becomes unlivable. The first year of the Falapili mobility pathway has exposed a harder question. What happens when an escape route begins drawing workers out of a fragile state faster than that state can replace them? The Australia-Tuvalu Falapili Union Treaty, signed in 2023 and in force since August 2024, created a pathway for up to 280 Tuvaluans annually to receive permanent residence in Australia. Visa holders may work, study, and access Australian health, education, and family support. Demand has been extraordinary. According to an Australian Department of Home Affairs report, the inaugural ballot attracted 2,474 primary registrations, representing 8,750 people when spouses and dependent children were included. The full allocation of 280 visas was granted for 2025-26, and Australia proceeded with a second ballot in 2026. These figures alone do not prove that Tuvalu is being emptied. The annual ceiling includes family members, meaning it does not represent 280 workers. Visa holders are also free to travel between Australia and Tuvalu, and migration can produce remittances, education, and professional networks that benefit those who remain. In addition, Australian officials have argued that random selection prevents the program from favoring Tuvalu's most educated applicants. The ballot is designed to reduce institutional and gender imbalances. Yet random selection does not prevent a randomly chosen essential worker from leaving.
Tuvalu is a country of about 10,000 people. Its workforce resilience cannot be assessed using assumptions designed for Australia. A large state can absorb the departure of a dentist, journalist, or specialist technician. In a Pacific microstate, losing one qualified person may mean losing a substantial part of an entire profession. Tuvalu's staffing crisis predates the visa. The government's 2025-26 civil service report listed 1,360 established positions, of which 343, roughly one quarter, were vacant. The report described persistent recruitment and retention problems. The vacancy rate rose from 21% in 2022 to 27% in 2023. 32 officials resigned during the reporting period, compared with 5 who retired. The Falapili mobility pathway should therefore be understood not as the cause of a new crisis, but as a potential force multiplier for an existing one. In Tuvalu, many public services depend on a very small number of qualified professionals, meaning the loss of even one nurse, teacher, technician, or senior administrator can create a national-level gap. The Falapili pathway's lottery system may avoid openly selecting the most educated applicants, but it does nothing to protect critical occupations. A random migration scheme can therefore produce highly uneven consequences, manageable for Australia, but potentially destabilizing for a state whose institutions already struggle with vacancies, recruitment, and retention. Individual decisions to migrate are entirely understandable. Better salaries, schools, and healthcare are precisely what make the pathway valuable. But those advantages also make permanent settlement more likely than the treaty's language of circular mobility suggests. Circularity is a legal permission, not an economic incentive.
A professional who is allowed to return to Tuvalu may still be unable to justify returning to lower pay, limited housing, and an understaffed workplace. Without funded positions and credible career pathways at home, skills circulation risks becoming a diplomatic phrase for one-way migration. Australia's own Tuvalu development plan reveals this imbalance. Its publicly listed indicators count visas delivered, settlement experiences in Australia, and increases in remittances. They do not establish similarly clear targets for retaining Tuvaluan health workers, teachers, engineers, or civil servants, or for measuring whether essential services in Tuvalu deteriorate after each intake. This is the central weakness of many Western climate mobility frameworks. They measure successful departures, but rarely measure the institutional capacity left behind. A visa can protect an individual while making the remaining community less capable of surviving the climate threat. The imbalance also carries geopolitical consequences, as the Falapili Union requires Tuvalu to reach mutual agreement with Australia on certain security and defense relationships with other states. If workforce losses leave Tuvalu increasingly dependent on Australian personnel and technical assistance, migration could deepen the power asymmetry already built into the treaty. The answer is not to prevent skilled Tuvaluans from leaving. That would force essential workers to bear the cost of national survival. Instead, Australia should attach a guaranteed mobility dividend to every intake, funding to train replacements, salary supplements for scarce occupations, and paid fellowships enabling diaspora professionals to return for fixed periods.
The treaty's Joint Committee should also publish an annual workforce impact assessment and adjust the intake when staffing in health, education, utilities, or public administration reaches critical levels. The Falapili Union is a groundbreaking expansion of choice for Tuvaluans. Its success, however, cannot be judged only by whether migrants settle safely in Australia. Mobility with dignity must also protect the right to remain and ensure Tuvalu's institutions do not disappear before its islands do.
Olya K-Mehri leaves you with the quiet image of a Tuvaluan hospital missing a nurse or a school missing a teacher, all because of a well-meaning lottery ticket. The fragility of a tiny island nation is exposed not by rising water, but by the escape route designed to save its people. Turning to Christian Elliott, that same sense of unexpected collapse scales up to the physical earth. Elliott isn't looking at civil service vacancies. He is looking at the literal ground giving way. Read alongside K-Mehri, Elliott's reporting on crumbling mountains in Greenland and Alaska feels like a brutal physical echo of Tuvalu's institutional drain. Notice how both writers look past the obvious threats of a warming planet to spot the secondary shockwaves. K-Mehri shows how a climate migration policy can accidentally empty a country of the people it needs to function. Elliott reveals how melting permafrost is ungluing the bedrock of the Earth, triggering 660-foot tsunami waves from collapsing cliffs. The shared realization is unnerving. Structures long assumed to be permanent, whether a national workforce or a mountain range, are already coming apart in ways nobody prepared for.
Climate change is moving mountains. As glaciers melt and rainfall grows more extreme, once stable lands are shifting. On geological timescales, the Earth is a dynamic place. Tectonic plates shift, continents move, mountains rise and fall. But during humanity's tenure on Earth, the ground beneath our feet has largely stayed put. That stable period may now be at an end. Climate change began in the atmosphere, where greenhouse gases accumulate, trapping heat from the sun. The planet's waters reacted. Precipitation patterns shifted, glaciers and ice caps began melting, the ocean generously sponged up heat and carbon dioxide. When the Earth's waters shift, so does solid ground. Now warming is destabilizing land across the planet, and geology is becoming a real-time science. In more and more places, the floor is giving way. In Alaska, Norway, Greenland, Chile, and New Zealand, as well as across the European Alps, mountains are crumbling. As glaciers retreat, some at unprecedented rates, they leave behind unstable cliffs that were once supported by ice. In 2023, one collapsed into a fjord in Greenland and generated a 660-foot wave that sent ripples through the earth detected on monitoring stations worldwide for 9 days. In Alaska last year, a landslide-generated tsunami struck in a fjord frequented by cruise ships. In Switzerland the same year, part of a mountain glacier detached entirely, burying the village of Blatten in a cataclysmic landslide. In the past decade or so, scientists have collected enough dramatic examples of this phenomenon to suggest that they're clearly not isolated incidents, but part of a pattern linking the loss of glaciers with landslide risk. And those landslides could get larger.
When the glaciers melted after the last glacial maximum, about 20,000 years ago, the landslides that followed were orders of magnitude larger than any we've seen in recorded history. But because some of today's glaciers have persisted in the landscape longer than those of that glacial period did, they've had time to carve steep, unstable cliffs. This means that we haven't seen the upper downs of landslides yet, Christian Elliott, a geologist at the Geological Survey of Denmark and Greenland, told me. In Arctic regions in the near future, the magnitude of landslides could exceed any scientists know of in the geological record. Along with glaciers, permafrost holds mountains together at high altitudes and latitudes worldwide. It too is in retreat, as scientists predicted in the 1980s, and as has now become apparent across the Arctic reaches. In the Brooks Range, home of the Trans-Alaska Pipeline, long frozen mountains have started to spontaneously deform and collapse within the past few decades or so, as their permafrost glue gives way. We're pushing these mountains into a state of disequilibrium, where they need to adjust their slopes in order to match the climate of today, the independent Alaskan geologist Brentwood Higman told me. They're essentially too steep for this warmer temperature regime. As a geologist, I found it shocking how widespread the sudden increase in landslide activity is, Higman said. When you're used to thinking on scales that span tens of thousands of years, to see these changes play out over human lifetimes, it's very dramatic. The thawing of permafrost in mountainous regions already threatens infrastructure. Denali National Park is close to finishing a $100 million bridge that will span a moving permafrost landslide. In the Brooks Range, engineers are pumping refrigerant underground to refreeze permafrost and stabilize pipelines. And mountains aren't the only land giving way. Cement-solid Arctic ground is turning into bogs. Communities across Alaska have had to relocate as their homes, fuel tanks, sewage lagoons, and garbage dumps tip, spill, or sink. Elsewhere, as massive underground chunks of ancient ice melt, the surrounding earth collapses into the voids left behind, buckling roads and swallowing buildings. In Siberia, once trapped methane explodes from under permafrost to cause 100-foot craters. When permafrost thaws, it changes everything. Sue Natalie, an Arctic climate scientist at the Woodwell Climate Research Center, told me. Natalie and her colleagues are seeing the thaw speed up, too. That is not a maybe thing, and it is not a local thing. It is a pan-Arctic thing, she said. Climate is also shifting the land at lower latitudes. A warmer atmosphere holds more moisture, which means more frequent and extreme rainfall events. In recent years, scientists have begun modeling how this kind of rain will increase landslide risk and linking individual events to storms made more dramatic by climate change. Harder, more intense, longer duration rainfall has a greater possibility to generate landslides, Jonathan Gott, who leads the United States Geological Survey's Landslide Hazards Program, told me. These kinds of debris flows and mudslides now threaten more communities. In North Carolina, Hurricane Helene triggered more than 2,000 landslides in a week. In California, slopes wiped clean by logging and drought-fueled wildfires slough away after heavy rain. One mudslide in Montecito destroyed 100 homes and killed 23 people in 2018. Landslides already cause $20 billion in damage globally, and that cost will only climb with climate change. Already, scientists have been able to catalog the effects of melting glaciers, thawing permafrost, and extreme rain. Other dramatic consequences of shifting precipitation patterns, volcanic eruptions, and earthquakes are only just coming into focus. More than a decade ago, in his book Waking the Giant, the University College London volcanologist Bill McGuire compiled decades of paleoclimate research to predict that climate change could lead to more volcanic eruptions and earthquakes. An increase in volcanic and tectonic activity would be a natural response to the end of a glacial period. For thousands of years now, the Earth's crust, which was weighted down by ice, has been slowly bouncing back. That process releases pressure from long-subdued faults and volcanoes, such as those in Iceland. Human-caused climate change is only accelerating these processes. And water, whether from extreme rainfall or glacial melt, can percolate in cracks underground to increase pressure on rock and reduce friction along faults, triggering both earthquakes and volcanic eruptions. Last year, researchers in Switzerland and France found some of the clearest evidence so far that glacial melt could indeed be affecting seismic hazards in high-altitude regions. After a period of intense glacial melt in 2015, a series of small quakes struck the Grandes Jorasses on Mont Blanc Massif, on the border of France and Italy. The probability of a 3.0 magnitude earthquake rose by 10 times, Tony Kraft, a seismologist at the Swiss Seismological Service at ETH Zurich and one of the authors of a related paper, told me. These quakes are still small, but they could trigger rockfall events that are already on the rise across the Alps. Falk Amelung, a geoscientist at the University of Miami, has also argued, somewhat controversially, that climate-driven extreme rainfall might have led to the dramatic 2018 eruption of Hawaii's Kilauea volcano. Scientists have not been able to find an obvious triggering mechanism for the eruption, and Amelung hypothesized that rainfall had infiltrated the volcano's edifice and increased pore pressure in the rock, kilometers down, to the highest rates in almost 50 years. USGS volcanologists were unconvinced. A link between heavy precipitation and some types of volcanic activity is widely accepted, but some scientists still reject the theory that an eruption such as Kilauea's could be caused by water reaching the magma below. If Amelung and others in his camp are right, though, as many as 700 volcanoes could be at risk of dome explosions and flank collapse over the next 80 years, he calculated. The system must be heavily stressed in a way that it's close to breaking anyway, he told me, and then this small stress change due to water brings it over the edge. During Earth's long history, small perturbations have caused millennia-long swings between hothouse and icehouse conditions. The amount of carbon dioxide that we have pumped into the atmosphere at a higher rate than ever before in Earth's geological history is a pretty significant perturbation, which then causes its own significant perturbations. The crust is not isolated. It's always connected. The climate, the fluid layers, the solid layer, you cannot separate them. Benedict Soya, a geoscientist at ETH Zurich, told me.
The atmosphere, ocean, and land are interacting systems, and their fragile equilibrium is reacting together to the stress we've put on them.
What lingers after these stories is the sound of bedrock cracking, or the quiet of an empty island clinic. A warming planet brings the sudden loss of things assumed to be permanent. Both the physical Earth and the daily routines of a community can fracture under the weight of invisible shifts. The question left sitting in the dust of these changes isn't about global carbon policy. It is something much closer to home. When the foundations finally give way, how do people decide what to save and what to leave behind?